Welcome to today's lecture, April 3rd, on higher order linear differential equations with constant coefficients. We're going to review how to find the general solution to these equations. So first we're going to review three cases, then we're going to construct the general solution. So there's three cases for the roots of the characteristic polynomial. We have a linear differential equation with constant coefficients, homogeneous differential equation, it has order n, meaning the coefficient of the nth derivative is non-zero. All these coefficients are real numbers. We construct an associated characteristic polynomial and the associated characteristic equation, setting the characteristic polynomial equal to 0. There are three cases for the roots of the characteristic polynomial. One is that all roots are real and distinct. The other is that some roots repeat. The third is that some roots are complex, not real. So we've seen this all before, but I wanted to go over the general case that can happen in each case and how we can construct a general solution. So notice in each case, any root is always going to give a solution, y is equal to e to the rx. Now this solution might not be real valued, it might be complex valued. In the last lecture we saw to deal with complex roots. We do get complex valued solutions and we can turn those into real valued solutions. And the other thing is there's always going to be an n-parameter family of solutions to the differential equation that is called the general solution. Okay. So let's look at the first case of the characteristic polynomial having n distinct real roots. So this is actually the simplest case because in this case we get an n-parameter family, just set e to the rx. Those are all linearly independent solutions. Each one's distinct. We form an n-parameter family of solutions to the differential equation, and that's actually the general solution. A general solution means that any solution of this differential equation can be written in the above form. That is, it can be written as c1 times e to the r1x plus c2 e to the r2x plus cn e to the rnx. So this is pretty straightforward. If you get n distinct roots of a polynomial that has degree n, then you just form those n distinct solutions. You get n-parameter family of linearly independent. All the solutions are linearly independent. You get an n-parameter family, and that is your general solution. The next case is repeated roots and multiplicities. So let's assume that r minus r1. Let's assume that our polynomial looks like a polynomial times r minus r1 to the nth power. So here, q of r, actually, it does not have r1 as a root. In this case, r1 is said to be a root of p of r of multiplicity m. And we get the following m linearly independent solutions. E to the r1x, so we've seen that before, right? If r1 is a root of the characteristic polynomial, e to the rx is also going to be a solution. Now, the other solutions we'll see, just keep multiplying this e to the r1x by higher and higher powers of x until you hit m minus 1. So you're not going to get all the way to m, you're only going to get to m minus 1. So for example, if m was 2, we saw that before, you get e to the r1x and x times e to the r1x. If m was 3, you'd get e to the r1x, x times e to the r1x, and x squared times e to the r1x. From these linearly independent solutions, there's m of them. Remember, we started at e to the r1x, and then y2 of x was x times e to the r1x. We form an n-parameter family, c1 plus c2x, all the way up to cm times x to the m minus 1 times e to the mx. Now, it's also possible you have more than one repeated real roots. Again, here, q, this is a polynomial, but it does not have r1 nor r2 as a real root. And in this case, we get an m1 parameter family, c1 plus c2x plus all the way to c, that should have been a subscript, cm1 x to the m minus 1 times e to the m1x, and m2 parameter family, c1 plus c2x plus all the way to cm, the parentheses is in the wrong place, or cm2 times x to the m minus 2 e to the m2x. Okay. So the next thing can happen is that some roots are complex, not real. So that means in this case, they come in conjugate pairs. R is a plus bi. R bar, the conjugate is, that should have been a minus bi. They're both roots of the characteristic polynomial. And a here is non-zero. In that case, e to the ax times c1 cosine bx plus c2 sine bx will always be a two-parameter family of solutions to the associated differential equation. And it's also possible for these two complex roots, the two conjugate pairs, to repeat m times. If a plus bi repeats m times, a minus bi will also repeat m times. And you can factor actually this polynomial. So this complex root, these pairs of conjugate pairs of complex roots correspond to solutions of this polynomial, r squared minus 2ar plus a squared plus b squared, or equivalently, r minus a plus bi times r minus a minus bi. And if they both repeat m time, you can factor out some polynomial with real coefficients, q of r, that's going to have degree n minus 2m. And then what we're left with is r minus a plus bi, the complex root, to the nth power, times r minus a minus bi, its conjugate to the nth power. In this case, we get a 2m parameter family of solutions. E to the ax times c1 through cmx to the m minus 1 times cosine bx. So it's the same thing. You just keep multiplying e to the ax times cosine bx by higher and higher powers of x until you get to m minus 1. You don't get up to m, and the same thing for sine. So notice here, right, there's two different complex roots, each of which are repeated m times, and you get a 2m parameter family of those. So if we have a complex conjugate pair that appears as a root of the characteristic polynomial, we get a 2m parameter family of solutions. Let's see how this plays out to construct an n parameter family of solutions. So you can always factor, this is true for any real polynomial, even actually any polynomial with complex coefficients even, you can factor out a real number. Well, okay, I guess if it was complex coefficients, this a could be complex, but for now, p of r has real coefficients. You can factor the real number, r minus r1 to the m1, r minus r2 to the m2, that should have been m2, not r to the m2, times r minus rk to the mk. r1 through rk are distinct complex numbers, and a is a real number. And these powers, the multiplicities, will always add up to the degree of the characteristic polynomial. Now these multiplicities, these powers, are not necessarily distinct. Some of them could repeat. Now if we have a real root and it appears mj times, it appears as multiplicity mj, we get an mj family of solutions, right? We've seen that just from case 2. If we have a complex root, then r minus rj to the mj power and r minus bar rj, its complex conjugate, those will both be factors of p of r, and we get a 2mj parameter family of solutions. And so notice when we had rj was a repeated real root and a repeated mj times, we get an mj parameter of solutions. If we have two roots, each of which can repeat mj times in the form of a conjugate pair, we get a 2mj parameter family of solutions. And we can combine all these together. So for this m1, we'll get m1 parameter family. From this m2, we'll get m2 parameter family, and so on and so forth. You can think of this actually as giving you, okay, this conjugate pair, this first one giving you an mj parameter family, and this one giving you another mj parameter family combined into a 2mj parameter family. Add all those up, you get n linearly independent solutions, as well as an n parameter family of solutions to the differential equation. Just combine those, and that's the general solution. So that's how to construct n parameter family of solutions, regardless of what your characteristic polynomial looks like. Okay, so that should be somewhat review. I realize I didn't go over the general case before of repeated roots, but it should be clear now. And you will be having some problems like this on web design coming up for practice. Okay, I will see everyone on Monday.